Greetings everybody. So we are continuing our videos on chaos-based image encryption, and the topic of today's video is pixel correlation analysis. So first of all, let me remind everyone a little bit about chaos-based encryption. The whole point in chaos-based encryption is to use a chaotic system, either continuous or discrete, but we generally prefer discrete systems in order to encrypt some sort of plain text information, whether it is some sort of data like sound, video, or image. And in this case, we are going to consider an image. So, we are going to encrypt this data to make it indecipherable so we can safely transmit it to a public channel. And then during the receiver end, we are going to reverse the whole encryption process to decrypt the information and obtain the original plain text information back. And to do so, of course, we are going to use the same chaotic system that we used during the transmission. And for this, we are going to use the exact same keys. And by keys, of course, I mean initial conditions and parameter settings. So this is the premise of chaos-based encryption, of course. And, for encryption, usually there are two main processes considered. The first one is permutation or shuffling. And this is the first process in which we take, for example, an image data, and what we do is we shuffle the pixels of the image. And the whole point is to disperse information throughout the whole plain text. So, as we will see in later videos, the image will become more resistant to attacks like cropping, for example. But the main part here is to practically disperse the information throughout the whole image. And the second step, which is actually the even more secure one, is the substitution step. Here, this is the step in which we take a pixel value and we substitute it with another pixel value. This is the most commonly done through, for example, exclusive OR operation. And the combination of these two processes, which are the most standard ones used in encryption, gives us the final encrypted image. So after we perform encryption, of course, what we want to do is perform a series of statistical tests on the encrypted image to evaluate its performance. In a previous video, for example, we considered the histogram analysis. Now, the second statistical test that we perform is correlation analysis. Now, the whole point in correlation basically measures the similarity between two different time series. And here, since we have an image, what sort of time series we consider? We consider adjacent pixels. And the whole point is to check whether or not adjacent pixels have similar values or not. Now consider this. Let's say I take a photograph of some sort of, outside area like a hill or this Peppers image, for example. Naturally, in this image that conveys some sort of information, pixels that are very close to each other in the space of the image naturally will have very similar values. So as you can understand, in a natural image that we take ourselves, the adjacent pixels are going to have a very high correlation. The correlation is either going to be very close to 1, or in case they are negatively correlated, it's going to be close to -1. And this means that they have very close values, or negatively close values, okay? On the other side, in an image that looks pretty much like white noise, like an encrypted image, the pixels that are very close to each other are not going to have similar values, okay, because we have encrypted them, so they convey no information, they have no similarity to each other. So naturally, in an encrypted image, what we want to obtain is a correlation of adjacent pixels that is very, very close to 0. So let's see what happens. Now, for adjacent pixels, they usually consider 3 directions. They either consider horizontal adjacency, vertical adjacency, and they also consider diagonal adjacency. And we are testing the correlation for all these 3 sets of pixels. And for all these cases, we want the same result. We want the encrypted image to have a correlation in all 3 cases close to 0. Okay. So let's see what happens. Here I have, for example, a graph that shows the correlation between diagonal pixels, because you see that we have the pixels at position xy and the pixel value at position x1 plus 1, y plus 1. So we consider, of course, diagonally adjacent pixels. Now, in the original system, here we have this sort of scatter plot. You see that adjacent pixels have a value that is very close to one another. And this is why all of these random pixels that I checked in this original image, their pairs, they lie in the diagonal of this matrix right here. Not a matrix, this graph, I'm sorry. And this means that these adjacent pixels have values very close to each other. And this is why they lie near the diagonal. On the other hand, we see that once we shuffle the pixels of the image, this relation immediately breaks pretty much almost completely, because we see that the adjacent pixel values of the diagonal elements in the shuffled image, their values are not really related, and that's why they are dispersed all around the range of 0 to 255. Okay, so immediately we have a very good improvement on the correlation between the adjacent pixels. Now remember, these pixels are just shuffled. So what happens when I perform complete encryption by substitution? Okay, you see here on the last image that here we have complete uniformity of the correlation. We see that adjacent pixels have values that, as a pairs, they lie all around the interval of 0 to 255. Okay. We have completely managed to break any correlation between adjacent pixels. Okay, and this is the result that we want for encryption for horizontal, diagonal, and vertical pixels. Okay, and I have the results here also computed numerically. In a matrix, we see that in the original image for horizontal, vertical, and diagonal elements, the pixels have a very high correlation, very close to 1. Okay, and this immediately drops significantly for the shuffled image. But even more importantly, once we go to the encrypted image, we have very, very, very small value for the correlation. Okay, and this is an example of a very good result against the correlation analysis for an encrypted image. We managed to drop it to a point that it's almost 0.001. Okay, so very, very low. This is a very good result for us. And of course, I consider that for grayscale images, but the results should be exactly the same for color images. Here we have, of course, 3 different channels, red, green, and blue, and we want to test the correlation for horizontal, diagonal, and vertical for each individual channel. And if we do our process correctly, we should have the same result for all channels. Okay. So this is an example for all 3 channels, red, green, and blue. For diagonal elements, we see the same result as before. Very high correlation in the plain text image. That's why these pixel pairs lie in the diagonal. This breaks down a lot for the shuffled image, and it's completely broken down for the encrypted image. Okay, this is the result we want, and of course we want it for all the possible channels, all 3 of them. And I have the results again in a table for red, green, and blue. Again, for the plain text image, it is very high, the correlation for all 3 cases, and for horizontal, vertical, diagonal, it is almost close to 1. Once we go to the shuffled image, it gets significantly dropped down to values very close to 0, but even more so for the encrypted case, we are dropping even more closely to 0. Okay, so this is the desired result for chaos-based encryption and correlation analysis. Once you perform it either for grayscale images, or for plain text color images, you should always get this sort of result. Okay. So in our next video, we will continue our analysis by considering several other statistical tests that are performed in chaos-based encryption. So thank you very much.